Hi folks, welcome back to Physics with Captain Rod. In the previous video, I worked an example just like this where I described why we would use momentum to analyze it. And I calculated that using momentum conservation that if mass A hits and sticks to mass B with a velocity of 10 centimeter per second before impact, that the system would have a velocity of 5 centimeter per second after impact. Now, a key concept in analyzing that was we were able to set the momentum of the system before impact equal to the momentum of the system after impact. I'm making this video to kind of explore how the kinetic energy may or may not change for some impact problems. So what I want to do here is just take a look at the kinetic energy before impact. The kinetic energy over on the left, remember kinetic energy is 1/2 mv squared. And it doesn't even matter what the numerical value is. I'm just going to put m. We're going to have 1/2 m times 10 squared. This would have units, if I put this in units of grams and this in centimeters, our kinetic energy would have units of gram centimeter squared per second squared. The units are not important for this discussion. If we multiply this out, 10 squared is 100 over 2. We end up with 50 m, whatever that is. Again, that's going to depend on the mass. Let's take a look on the right. So that was before impact. Here's after impact. If I were to calculate the kinetic energy after, we're going to take a look at this. We're going to get 1/2 m. Now remember that over here it was just m, but this system has twice the mass here, so I'm going to put 2m times 5 squared, and again this will come out in units of gram centimeter squared per second squared. And this kinetic energy, let's see, these kill off one another. This is 25m. Now, the actual numerical value is not important, but notice that 50m, 25m. In this problem, the initial kinetic energy is greater than the final kinetic energy by quite a bit. And this is usually the case for impact problems. The reason is this. In order for these to stick together, they must have had Velcro or something like that. And Velcro, when it comes in contact with its other side there, when they kind of mate together, you have some deforming taking place. And anytime you deform material, the material gets hot. You can try to experiment if you want. Go grab a paper clip and bend it back and forth, and you'll find that that paper clip's temperature will go up. Anytime you bend material, that creates heat, right? It makes things warm. And basically what it does is it robs the system of kinetic energy. So as a rule of thumb, the kinetic energy before an impact, I'll call that KE1, is generally greater than the kinetic energy after an impact. Now you might wonder, can we ever put equality? Well, it turns out there are special cases where the kinetic energy is basically the same. And if you look at the mechanism I just talked about for changing the kinetic energy changes whenever you have permanent deformation of material. So in order to find a collision where kinetic energy is the same before and after, you're looking for collisions where there's no material deforming. Pool balls would be good examples of that. Pool balls barely deform at all, so they're very close to a kinetic energy conservation situation. In the atomic world, this happens a lot. You know, if you have a positively charged particle, this is something we'll talk about in physics too, you know, it runs into another positively charged particle. They'll both go moving off, and there'll be no permanently deformed material. So molecular impacts are impacts where kinetic energy is conserved or close to conserved. But for the most part, you're looking for impacts where there's very little deforming of material. Pool balls would be my first example, steel bearings, things of this nature. Now the good news is that, as I showed in my previous couple of videos, usually we can be clever about how we define our system. Usually if we define our system as kind of the whole kit and caboodle, usually the net force on that system is zero, and we will get a momentum conservation. And only sometimes will kinetic energy be conserved. So my advice is always this: when you're dealing with an impact, start with momentum, because you can apply momentum conservation without fear. But kinetic energy conservation only sometimes occurs. Usually it's not what we're going to want to use to analyze the problem. In a lot of problems, we'll calculate the kinetic energy before and after and kind of compare them, but usually we'll stay away from kinetic energy conservation within the problem itself. When you're working your homework, some clues that you could use energy conservation: if you see the word elastic or perfectly elastic collision, that is typically, or that means a collision where kinetic energy is in fact conserved. That helps as far as your homework is concerned. As far as reality is concerned, you're looking for physical examples where there's very, very little deforming of materials, such as pool balls and steel bearings. So anyway, hope this video helped. Remember, when you see an impact, use momentum first. You can always use momentum without fear. And if you can get it solved from that, great. If not, you consider using kinetic energy conservation. In your homework, you're looking for the word elastic to do that. Hope this video helps. Have a great day.